Hi everyone, this is Bryant. So this semester I did my project on the Tedlium Release 3 corpus and basically studied the neural network based language modeling. So basically, the motivation behind the original research paper and the portions that I replicated was obviously an automated speech recognition task, right? And so the corpus, as mentioned, is the Tedlium Release 3, which is 452 hours of transcribed TED Talk videos, which is more than a doubling, I believe originally 209 hours from the Release 2 corpus. And so we're going to measure the models based on a word error rate, which is effectively just the ratio of words gotten wrong to words gotten right. And then kind of the main model will be replicating is a hidden Markov model based, which is a model where there's a separate acoustic model which is responsible for parsing of the actual audio data, and then the actual language model itself, right? So the acoustic model being a TDNN, the time-delayed neural network, which we covered in class, which is effectively a one-dimensional CNN. You see the architecture there in the diagram in the top right. That's state-of-the-art. And then language model, which are originally based off of n-grams, but then obviously the state-of-the-art, more LSTM or GRU-based architectures, your recurrent neural network-based language models. Okay, and then so ultimately you can see the performance of kind of on the Release 3 corpus there with the n-gram based models. You can get as well as a word error rate of 7.7%, and then you can see the significant improvement once you move to an RNN-LM based language model of full percentage improvement. And what's interesting is that you see that with one of the things that they tried to test in the paper was, hey, is there material improvement in the models for the more than doubling the training data? And what you can see in the top right there is that for the HMM-based models, there's actually not a very material improvement at all. However, for a full neural end-to-end model, which I didn't have time to replicate in this study, but effectively you can think of it as the acoustic model steps, the language model steps. It's one big network. You have the first a few convolutional layers, and then you have a bunch of effectively RNN-based layers before you have like fully connected, softmax, etc. Right? So what you can see at the bottom right is from the original study is that although its best performance is not as good as the HMM-based model, you can see that it does have the drastic improvement from the increase in training data, right? So it implies that like maybe with even more training data, eventually the performance will surpass the other one. From there, further research I would have liked to have done had I, one, had more time, and two, just had more success getting some of this to work, right? Because some of it just didn't work. Is one, similar to kind of how in image recognition tasks, you use image augmentation to create more training data. It's been shown that you can do that for audio too by randomly perturbing like the volume and speed. So we'd like to try that. The vocabulary, I would have liked to have done more work with a subword of vocabulary, which is basically the stem. So rather than like having the present tense, past tense of a word be two distinct words of the vocabulary, you have the root word as one word of the vocabulary, and then you have like the ed at the end as like a separate subword, right? And it basically ties more the meaning of the root words of the vocabulary. And then ultimately, the fully neural model that they presented in the paper, I would have liked to have done be able to replicate that too, to replicate the results with the increase in performance with training data. So yeah, that was my project, and there's references. Thank you, everybody.